Okay, we're back for project 2. Me, Christopher, Dylan, and Noah, our cameraman for this part. First off, copper crystal structure. Copper is FCC, face-centered cubic. This is the most stable and one of the most common structures, as you can see from our beautiful picture. And atoms are closely packed and providing high ductility and electrical conductivity for FCC. Okay, so determining atoms per unit for FCC. Pretty much you get, your grand total is going to be 4 atoms for this. But to get that, first off, you have your 8 atoms times the 1/8 of an atom to the unit cell. There are 6 atoms at the center of the cube's faces. Each one is shared between 2. So that's where you get your 6 times a half here to equal to 3. And then when you add them up at the end, 1 plus 3 is your 4 atoms per unit cell for FCC structures. This is just your coordinate number for that is 12, which you can see from these images. FCC basic structures here.
All right, so here we have finding atomic packing factor. Specifically, here we have copper. I mean, atomic packing factor, you're finding just by taking the volume of the atom divided by the volume of the unit cell. Here's the math for it. You got to get the radius, the atomic radius of copper specifically. Once you do all of that, you just take the volume of the atom divided by that, and it's 74%. So 74% of the unit cell is occupied. Now, here we have finding the theoretical density of copper. To find that, you take the molar mass of copper, which once again, you need to be given that, which is right here. And then you're going to divide that by the volume that copper takes up, multiplied by Avogadro's number. Volume of the copper, there are spheres, so use that. You need the radius once again of copper. Then you can find the density, and the theoretical density we found is around 11,000 kilograms per meters cubed. Here's the crystalline direction families, 120 specifically for copper, and that's all of them. And then here we have the zinc crystal structure. It's an HCP structure. And then the atoms per unit cell. In an HCP structure, there's 6 corner atoms, so that adds up to 1, 2 face-centered ones, and then in total you're gonna have 6 atoms per unit cell. Oh, gotta go back. Oh, now here we have the coordination number. The coordination number is how many atoms are touching one specific atom you're looking at. So here, if we're gonna use this one for reference, you have 6 surrounding it here, touching that one, and you have 3 down here, and you have 3 more above it, which gives the coordination number of 12. And then here's finding the atomic packing factor for zinc. Same thing. I mean, volume of atoms divided by volume of the unit cell. But you have to use the area specifically of a hexagon that's hexagon shaped in order to get it. But this also ends up being 74% because it's the max atomic packing factor you can get. Then find the theoretical density. Same thing as copper once before. You need the molar mass, you need to find, which is here. Avogadro number, constant, radius of zinc, which you have to look up. And this one was about 10,500 kilograms per meter cubed. Then here's the 120 family for zinc.
Okay, for our alloy we have brass, and because brass is an alloy, it's made up of copper and zinc, it doesn't have one structure, it depends. So if it is, the zinc content is the main factor here, because if it's less than 35%, you have that FCC structure we saw with copper. If it's between 35 and 45%, it's either you have a mix of both the FCC and BCC from zinc. And if it's zinc is over 45%, it's just your BCC structure. So it depends because it's an alloy mixed up. For the BCC structure of brass, because we already talked about FCC, that'd be redundant. We don't want to waste time here. So for BCC, you have your 8 atoms across, times the 1/8 is where you get your 1 from. There's one atom in the center that you can see here. So when you calculate this, you get 1 plus 1, simple 2 atoms per unit cell. Go down.
So this is the brass family FCCs, and they're all right here. This is the negative, this is the positive. So crystal structure for GAS is primarily crystallized into two forms of zinc blended structure, cubic and a hexagonal structure, so which are both structured similarly as FCC structures. And FCC, as we stated before, it's the most stable and common crystal structure of copper. Each copper atom is positioned at the corners and face centers of a cube. In FCC structures, atoms are closely packed, providing high ductility and electrical conductivity. And we find the 4 atoms per unit cell. And then here's the GAS family right here. And then for the crystalline plane family of 111, we have the equivalent planes right here.
For our plane structure here, because it's 111, these are equivalent planes. This notation above means negative, and that's how it is. And then over here, you can tell this is 111 because where's the intercepts on each axis? X1, Z1, Y1. Oops, let me go back quick. And that's where you get your plane come out. Like if this was X0, you see that back in, and it'd be a new plane. So the 111 plane is accurate right here.
Okay, so for the final thing, this is how we go about finding the linear and planar densities of all 3 structures that we have here. First, we'll start off with the linear density of an HCP structure. So linear density in general is number of atoms divided by the length of the vector created. So length will be equal to the magnitude of HK and L being 1, 2, 0 here. So the length of the vector for all of these is going to be radical 5. Number of atoms in an HCP structure on that vector is going to be 2, so it's going to be 2 over square root of radical 5 times A for an HCP structure. For an FCC structure, 1 atom, same length once again, so it's just 1 over radical 5 times A. BCC structure, it's the same thing as FCC, so 1 over radical 5 times A. Now for finding planar density, you're finding the number of atoms divided by the area of the plane given. So we'll start off with HCP again. HCP, there's 3 atoms on the plane, and then finding the area specifically in HCP1, you have to use the area of a hexagon again, which is just 3 radical 3 divided by 2 times A, which is going to simplify out once you do all the math for it, 2 over radical 3 times 3, which then can just become, actually no, it's just 2 over radical 3 times A. Then you're gonna come over here for planar density of an FCC structure, 3 atoms, and then you're gonna use radical 3 over 4A, which becomes 12 over radical 3A. And then finally for a BCC structure, you have 3.5 atoms on that area given. Then the area itself is radical 3 over 2, which simplifies out to 3 over radical 3A.